right, so we're gonna go over the fluid mechanics in the side pod of a race car real quick. So what exactly is a side pod? So it's gonna be this region here shaded in yellow, all along here. You're gonna see this on all sorts of open wheel racing vehicles, whether that be IndyCar, F4, all the way up to F1. You'll see it on some Formula SAE cars as well. There's all sorts of things. It's a very kind of standardized practice. You'll even see kind of similar things in non-open wheel cars in IMSA. This is a very good way to effectively move the air where you need it and get your cooling down how you need it. So kind of the governing equations here. So the big ones are going to be your conservation of mass, and then we're going to rearrange Bernoulli's in a way that we can use it, and that's going to be solving for a delta P. So you're going to have this P2 minus P1 is equal to 1/2 rho, and then parentheses V1 squared minus V2 squared, and then you're going to have a minus delta P. So these losses that delta P losses are mostly going to be due to friction along the walls of the side pod. Where there's not really a whole lot of height variation that you see from the side pod, so we can kind of neglect those gravitational effects that we would normally see within Bernoulli's. So these delta P losses are usually going to be represented with a K, and we'll kind of cover that here in a little bit when we do a work example. So here are some of the assumptions that we're going to use. So we're going to say race speeds are going to be maximum around 220 miles an hour. And we want to do the maximum just because we need to know our Mach number. It's going to be less than 0.3. It came out to around 2.8 or 0.286. So we can assume incompressible flow, which is really nice for solving this equation. It makes it a lot easier for us because Bernoulli kind of comes a little weird once we get into compressible flow regions. Although temperature and elevation does differ around various tracks, we're going to kind of assume same air density at sea level of 1.225 kilograms per meter. This is also about 25 degrees Celsius. We're also going to neglect some heat transfer effects on the air just for ease of simplicity. Makes things a lot more difficult, and we'll kind of get into that a little later when I cover that part. So here's kind of the visualization of the inside of the side pod. It's very important to have like a representation of this. So this is going to be kind of the front here. This will be your inlet. You can't really see it there, but this air is going to flow in and into this radiator here. The radiator plays a crucial part. I'm going to show a CFD video here in just a moment that models it without a radiator, but it does show kind of some overall governing Bernoulli's effects. All right. So here you can see this model. So you're going to have your small entrance here. This is going to speed up your velocity, drop your pressures, and then it's going to further slow down here and then speed back up on the exit. So there's some things missing here. Obviously the radiator will create a very large high pressure zone that helps draw the air through the radiator. But the main things I wanted to show here are these kind of just typical Bernoulli's effects of an increase in speed here, increase in speed here, and then an overall decrease as it converges. And then I also wanted to point out these lines on the edges are moving very, very slow, and that's due just to friction, and we know that velocity on a surface is always 0. So wanted to point that out.
So we're going to break down the race car side pod real quick for this project. Conveniently enough, there's one right here. So this is your whole side pod. This is where all the cooling and the magic happens. So taking you kind of from front to back here. So front side, you have this real small inlet. That's going to speed up your air as it passes through. So you have your like static pressure out here. It's going to speed it up, and you're going to get a pressure drop through the radiator. And then somewhere about like right here, you're going to encounter that radiator. You're going to create like a really high pressure zone on that front side. So it's counterintuitive because you kind of think, oh, well, there's a low pressure zone at the front side. There's a really high pressure zone here. It's going to want to work backwards. But the way to get around that is we converge here again, create another really small spot there. It's going to speed that air up, drop your pressure again. So this backside here has a very low pressure even just compared to this front side. So that's going to produce flow throughout the entirety of the system and get it through very nicely. So that way it doesn't stagnate in front of your radiator and all that. So there we go.
Kind of a worked example. I kind of chose some velocity values that we know, as well as some like loss values that are typical for a side pod. So we're going to have our V1, our V2, and then that KL is going to be our losses. Assumed an air density of 1.225, and then we have a velocity through the radiator of 20 meters per second. So when doing these calculations, you kind of have to calculate Bernoulli's twice. So that's what we're going to do here. So first off, we're going to calculate our V squared for V1 and V2. We're going to subtract those to get our delta V, and then multiply it times the 1/2 density, and that's going to be our pressure change for our dynamic flow, basically our converging, diverging sections, and that's going to be 1653.75 pascals. And then we're going to calculate across the radiator. So 1/2 times density square of 1/2 times density times velocity squared of the radiator. That's going to be this 20 meters per second here. It's going to give us 245 pascals. We're going to multiply that times our losses, mostly due to friction, like I said. And that gives us kind of this 490 number. Add that with the delta P for the dynamic flow, and it comes out to about 2.14 kilopascals. From the research I've done, this is a very standardized value, pretty typical for a side pod. So I really wanted to reassure my data and make sure that this was a kind of typical value for a pressure drop all the way across. So this is going to show that air is going to be moving through the side pod and the radiator, which is really good because that mass flow rate through the radiator is a big part of cooling when you get to your heat transfer equations and everything. So now to talk about those like pesky considerations. So we assumed a constant temperature throughout the system. Due to the heat transfer, the whole point of a radiator is to take the heat from the radiator and warm up that air, therefore cooling off the radiator. So this heat transfer is going to have some density changes as well as some pressure changes, which is then in turn going to change your velocity and whatnot. The radiator also adds a lot of friction into the system, further heating up the air. They're, depending on the type of radiator you can have very high fin densities, which is basically just air flowing over a bunch of surfaces, and we know as it flows over a surface, there's a lot of friction created. So yeah, that's it.